Okay, here we are with another wave interference problem. In this problem, we have two radio antenna, and we're told that they're 100 meters apart, and they are broadcasting identical radio waves. So they're in phase, right? Um, they're in phase at the beginning anyway, initially. And we're told the frequency they're broadcasting. Your job is to monitor signal strength with a handheld receiver. You can kind of imagine yourself doing that. To get to your first measuring point, you walk 800 meters east from the midpoint between the antennas, then 600 meters north. So, in case you haven't kind of tracked on that, we're looking at the way I have this drawn is kind of conventional here, where I've got north, south, west, east. And we're looking at this from top down, okay? Um, So the first part of the question here is what is the phase difference at this point, at point P, what we're calling point P here. So we want to, one of the things that would be really useful for us to do here is in order to find the phase difference, well, let me write out our equation for phase difference to remind us what's useful. So our phase difference, 2 pi delta R over lambda. Okay. Um, and this is for starting out with in-phase sources, which we have here. So what this tells us is that we need to figure out our delta R, which we can, and then we need to figure out our lambda. So let's do both of those things. So our R sub, I'll call this one here from antenna A, I'll call that R sub A, and from antenna B, I'll call that R sub B there. And you can create right triangles here and solve for both of those there. And I'll go ahead and execute this problem numerically. You can do it symbolically, but I would hold on to the proportions there. I've done this symbolically in class before. And for instance, the 100 meters between A and B, I'll call that D. And then I'll call, instead of 600 meters, call that 6D. Instead of 800, call that 8D. And what that does is it kind of keeps the original proportions of the problem intact. Otherwise, sometimes the problem can change or become very unphysical. So anyway, R sub A, we can solve for that just by solving for a hypotenuse of a triangle there. And that will end up being, let's see, let me write this out just so you guys can follow along. So that'll be 800 meters squared plus 550 meters squared. So for R sub A, we end up getting something around 971 meters. R sub B, we'll do the same kind of thing. Make sure that you trace out those right triangles so that you can kind of make sense of what you're doing. 800 meters squared, and this one and then will be 650 meters squared. And for RB, that gives us 1,031 meters. So our delta R, which is going to be RB minus RA, is equal to about 60 meters. So we've got that. It's supposed to be my about. And then I can solve for the wavelength of this wave. That's just going to be the wave speed divided by the frequency, given the wave speed here these are radio antenna, right? So that's going to be what we call speed of light, but it's basically speed of electromagnetic radiation here. 3 times 10 to the 8 meters per second. That's a nice number, divided by the frequency. And we're given the frequency is 3 megahertz. So that's 3 times 10 to the 6 hertz, which gives us a wavelength of 100 meters. Cool. That allows us to solve for that phase difference at point P. So the phase difference at point P is going to be 2 pi times my delta R, which is 60 meters, right? divided by wavelength, which is 100 meters. So that gives me 1.2 pi radians. Great. And I expect that to be in radians, right, when it comes to your phase difference stuff. Okay. Part B asks, how would you describe the interference at this point? Like, what does that interference look like? Well, we could figure that out by looking at that phase length, that phase difference, right? So if I look at my phase difference here, a way that I can write this is 1.2 pi radians. So that's actually 2 pi times 0.6. And this 0.6 tells me that we're somewhere in between constructive and destructive. We're neither an odd multiple of half a wavelength, right? And nor are we exactly wavelength. So we don't have constructive, we don't have destructive. We're somewhere in between there, that 0.6 of a cycle there. Okay. So part C says, if you now begin to walk farther north, so imagine yourself walking like upward on the page here, does the signal strength increase, decrease, or stay the same? Then it says there, explain. So we can just check a point that's farther north. And all I did was I just went north by like 10 meters and I checked a point right above there. So there are different ways to do this, but that was kind of how I chose to do it. So what I say here is move 10 meters north. And if you move 10 meters north, what you'll get then is for your RA is you'll get, so my 800 stays the same, right? But now I've got 560 meters squared, and that gives me something like 976. We can calculate RB here. Again, my 800 hasn't changed, but now this is 660 meters. So that gives me 1037.1-ish meters. So my delta R, that's still RB minus RA. My delta R is now 60.61 meters. And my phase shift at the point where we're reading the meter, right, is equal to 2 pi, now 60.61 meters. So that number has changed. Over 100 meters, wavelength doesn't change. And this gives me 2 pi times 0.606 radians. Okay, so basically I went through the same analysis. I moved 10 meters to the north. They're asking me what happens to the north. Does it increase or decrease? I moved 10 meters to the north and I wanted to see what happens. So I did the same analysis. So we can see here, because the phase difference is increasing, right? So when we look at this phase difference, it has increased from before. As you move north, you're moving from a destructive toward a constructive condition. So the signal strength is going to increase there.